We said that trying to find a lower bound is actually quite a bit trickier than finding an upper bound. And here's an example of why that's the case. This is a valid binary tree, right? Because our condition for binary tree is that each internal node can have at most 2 children, right? And that's true here, right? So here are the internal nodes, and they are filled in, okay? And the number of children for each one is just 1, right? So it has 1 child, the second one has 1 child, the third one has 1 child, and so on. And so that makes it a valid binary tree. It looks a lot more like a linked list, but that's kind of the point. Linked lists are actually a special kind of binary tree. They're just not very useful as binary trees. So what we have is 1 leaf, right, and 4 internal nodes. So you can see that it's not really easy to find a lower bound, right? I mean, the lower bound could be 1. Every non-empty tree has to have at least 1 leaf. Not useful, okay? So we need some kind of conditions to prevent this kind of disaster from happening, okay? And we can do that, okay? So let's define a full binary tree, okay? Now, a full binary tree is one in which all internal nodes have exactly 2 children, okay? Now, be careful. This is something else that I could have said, okay? This is the binary tree where all the leaves, right, are at the same height. Okay, and that's not what I said. Okay, so sometimes when people think of full binary tree, this is what they think it means, but that is not what we mean by full. Okay, of course, this particular tree is full, right? Because every internal node has exactly 2 children, but it's more than full, okay? It's full and complete in a certain sense, meaning that we force every node that's high up in the tree, right, that's not at the very bottom, to actually have 2 children. So this guy here has 0 children, right, is a leaf. If I actually had kind of a complete tree, it would be forced to have children, and that's not what we mean by full, right? So be careful, right? A lot of people kind of misinterpret that word, okay? So if we have a full binary tree, then what can we say, right? Notice that this prevents me from doing this, right? Like I did in the last slide, because this has only 1 child, right? And so that would be a big no-no. It would have to have at least another child, right? And that brings me back to this tree, okay? All right, so how can I use this to give me a bound? Well, notice that I can pair up every leaf with its parent, okay? Then I'm left with this kind of lonely leaf over here, okay? So what does that tell me? That gives me a relationship between the number of internal nodes is actually equal to the number of leaves. Close, right? Is the number of leaves minus 1, right? Because we have, 4 internal nodes and then 4 leaves that are matched and then this extra lonely leaf, okay? So one of our measures is the number of nodes, okay? And that's equal to the number of internal nodes plus number of leaves. But we know what that is because the number of internal nodes is just the number of leaves minus 1. So this is twice the number of leaves minus 1. Okay. Now here is kind of the big moment. Okay. That's true for this particular tree. But what happens in general? Okay. So I could add more internal nodes, right? And would that be bigger than the number of leaves minus 1 or smaller than the number of leaves minus 1? And actually what we have is smaller, okay? So what does that mean, okay? What that means is that if I know the number of nodes, right? Let's say that I know that I have 10 nodes, okay? Then the number of leaves can't be, for example, 3, right? Because if I only have 3 leaves, then I have 2 times 3 minus 1, and 10 is actually not less than or equal to 5. Okay, so this is why this is actually a lower bound, okay, on the number of leaves. Okay. So let's see if we can actually prove this. And by the way, you may not believe me that it's less than or equal to. Maybe you think that it should be greater than or equal to. That's okay. We're actually going to do a proof right now. Okay, so we're going to prove that this statement is correct. I'm just simply offering it as a possibility. Okay, so let's do it formally. Okay, so here's our statement of the theorem. T is a full binary tree, and the number of nodes is size t. That's just that function that we wrote. And then we have this restriction. The restriction is that size of t has to be greater or equal to 1. What this means is that it's not an empty tree. Okay, that hypothesis keeps coming up, right? I have to keep ruling out the empty trees, which is kind of a clue that maybe when we included those, maybe that was a mistake. Who knows? Okay. Anyway, we have that the size of the tree is less than or equal to twice the number of leaves minus 1. Okay. So let's see, right? So this time we're going to use induction on the structure of T. Remember, I said I was going to vary the induction just to show you different styles, right? So first we use induction on the height of the tree. Now we're going to use induction on the structure of the tree. This is structural induction, okay? So our base case is this is what a tree looks like, kind of the minimal tree, okay? Now usually, right, I would need 2 base cases, right? And that's just because we said that a tree could be the empty tree, or it could be a tree that just has a root node, right, and no children, or it could be a root node with children. That's the recursive case. The reason that I only have 1 base case is because of this statement, right? We already know that a tree is not empty. This theorem does not apply to empty trees. So our base case is actually just a root node that has no children, okay? Now, in that case, how many leaves does it have? 1, right? Well, how many nodes does it have? What's the size of the tree? 1. So yeah, it is in fact the case that the size of the tree, which is just 1, is twice the number of leaves, that would be 2, minus 1, okay? So yeah, they're equal, right? It's actually equal. I don't even need the less than or equal to, okay? All right, so that's good, okay? We got the base case proved, okay? What about the inductive case? Okay, so let's give it a shot. In the inductive case, what I have is that my tree looks like a root node, A, with a left subtree and a right subtree, okay? So the size of T is just 1 plus the size of TL plus the size of TR, the left and the right subtree. This is just by the definition of size, okay? In fact, it's exactly the definition of size once we know that we're dealing with a tree that has either a left or a right child, okay? Now here we have the induction hypothesis, okay? And this is less than or equal to here. And we say that, well, the size of the left subtree is less than or equal to the number of leaves in the left subtree minus 1. Likewise for the right subtree, okay? And once we use the induction hypothesis, the rest is just algebra. So we pull out the twice number of leaves, and then we have a 1, minus 1, minus 1, so we end up with minus 1, okay? Then we factor out the 2, and then we realize that the number of leaves of the left branch plus the number of leaves of the right branch is the same as the number of leaves of the tree. So indeed, size of T is less than or equal to twice the number of leaves of T minus 1. So that is yet another check mark. And since we've done the base case and the induction case, then we actually completed the proof, okay? You buy that, right? That seems pretty convincing. It is, okay? But there's one thing that might make you suspicious, okay? I said that this theorem required the tree to be full, and yet I never used the fact that the tree was full. And actually, didn't we see an example where the theorem wasn't true, and because it wasn't a full tree, right? Just a whole bunch of internal nodes and then the lonely leaf node. So where actually did we use this fact, right? If we didn't use it, then there must be a mistake in the proof, because we know that without it, the theorem isn't true, okay? Now, the answer to that is that actually we did use it, and we used it right here, okay, when we decided to do the induction hypothesis, okay? So at this point, we used the fact that T is full, okay? Now, why is that? Well, what I kind of assumed, right, was that the size of the left subtree is less than or equal to twice the number of leaves in the left subtree minus 1, okay? Now, how do I know that there's actually a left subtree? Well, I know that T has at least a left subtree or a right subtree because it's not a leaf, okay? Now, because it happens to be a full tree, then if it has a left subtree, it has to have a right subtree, okay? So that's actually the place that we're using that, okay? It really does have a subtree. And remember, that's important because if it was nil, then I can't use the inductive hypothesis because it only works for trees that have at least one node. Okay, so right here, very subtly, I'm using the fact that the tree is full. That's why this proof works. Now, as before, it turns out that ACL2 can prove this theorem by itself. Okay, so here's the statement of the theorem. I have three hypotheses. We're actually talking about a binary tree, so this is binary. And const tree, what that means is that it is not nil, okay, i.e. it is not empty. Right? And so that's similar to or equivalent to this restriction. And it's full, right? Okay, so in that case we know that the size of the tree, which is the number of nodes, is less than or equal to twice the number of leaves minus 1. And it solves it exactly how we did it. It'll use structural induction on trees, and it'll come up with yes, that's true. Okay, so we've done that. Can we actually get a lower bound? Okay, like for example, maybe I can compare the number of leaves to the height, right? Because that's we already did that in the opposite direction. We know that there can't be any more than 2 to the h. Can I say something about needing at least so many? Okay, well, I got to be careful because right here is a tree whose height, right, is equal to 4, but that has 5 leaves. Okay, so that doesn't really give me a very strong theorem, right? I mean, maybe I can prove that the number of leaves has to be at least the height plus 1, but that's just not a very strong result. So can we do any better? Okay. Now the problem is that again, this tree is a lot like a list. Okay. So if I simply ignore the internal nodes, I get 5 elements in a list, and just as an aside, this is actually the way that lists are constructed in ACL2. Think of the internal nodes as const nodes, right? And so I have an element, right? This is just like A1, and this side of the tree is like L1, and so I have const A1, L1, right? So this could actually be the way that trees are built. I mean, no, I'm sorry, the way that lists are built. So yeah, it's no good, right? This is where I need one more definition, okay? And this is a property of trees that will be useful. When we say that a tree is balanced, if in fact I can find some h, okay, and this h is sorta, okay, the height, okay. It's not exactly the height, okay, but you can see that it's very close to the height, okay. And what I need is to find an h that all leaves are either h steps away from the root. That's what I call the height of that leaf, or h minus 1 steps away from that root. So here I'm 0 steps away from the root, right? These nodes are 1 step away from the root. These nodes here are 2 steps, and then these nodes are 3 steps away from the root, and those are 4 steps, right? The height is the maximum of those, so it's actually equal to 4, okay? But no, and if I set h equal to 4, then I have some leaves that are at step 4 and some leaves in step 3, and there are no other leaves, right? They have to be in steps 4 or 3. So basically what we're saying is that it is balanced if in fact all the leaves are either at a distance height of t away from the root or height of t minus 1 away from the root, okay? That's really the property, okay? Now here, notice that I'm actually forcing it to have a lot of leaves, right? Because I can't just have kind of a lone subtree at the top that just has 1 leaf. It's, you know, they have to come all the way down. So that should actually help me prove some properties, okay? Almost, right? Except this can still happen. And the reason this can happen is that we said something about balance, right? So here I'm perfectly balanced, but I'm going straight down. And then I might branch out, right? And so this guy's over here, well, it looks just like the previous tree. So you know, there's still a 1, 2, 3, 4, but now I simply add 2 levels. So now it's 6 and 5 instead of 4 and 3, right? So you can see that I can make that, I mean, I can make that 6 million and, you know, 5,999,999 instead of 4 and 3. But there's no good theorem now, right? You know, because I don't have that many leaves, okay? So we need to somehow combine these two properties because I want both of them to be true. I want the trees to be not skinny, right? And I also want them to be fair so that one side isn't overpowered by the other. So I can just take both conditions. It is full and balanced, okay? Turns out I really need both of those. And this is what I mean. This is not the height, okay? not the height of the tree. Instead, think of this phrase, balanced with height h, right? So that's the h that I used to show that it was balanced, okay? So it's actually could be the height of the tree, or it could be one less than the height of the tree, okay? So, so let's see, okay? So in that case, the number of leaves has to be greater than or equal to 2 to the h minus 1. That's a strong statement. Let's see if we can make it hold, okay? So the base case, again, the base case means that I have a root with no children because the empty tree is not permitted, right? So in this case, h has to be equal to either 0 or 1. Now, why is that? What we said was that all of the leaves has to be a step either h or h minus 1 from the root, okay? So there's only one leaf, and it is a step 0 from the root, okay? So if h is equal to 0, I get it. If h is equal to 1, I get it because of the h minus 1, right? But any other value, it doesn't work, okay? So those are the two possible values of h. So we can do it, right? Because 1 is the number of leaves. That's actually greater than or equal to 2 to the 1 minus 1, which is 1. That's in case that h is equal to 1, right? And this is the case when h is equal to 0. Right? The number of leaves is still 1. When I have 2 to the 0 minus 1, that's 1/2. It's still true. So our base case holds. Okay? So let's see about the induction step. Okay? So in the induction step, what I have is, well, the number of leaves is the number of leaves in the left tree plus the number of leaves in the right tree. This is just the definition of number of leaves. Okay? And here's where we use the induction hypothesis. Okay, so we say that that's greater than or equal to 2 to the h minus 1 minus 1 plus 2 to the h minus 1 minus 1. Okay, now why is that actually true? Okay, I'm actually using this fact. I didn't prove this fact, but it's not particularly hard to prove. If I have a tree that is balanced to h, right, then the subtrees must be balanced to h minus 1, right? If that wasn't true, right, then it simply wouldn't work because I simply take away that top of the tree, right? So, you know, I look like this. So what I have here is a subtree, which is t sub l, and I have t sub r here, right? And this is 1 plus to the h, right? So this whole thing is h or h minus 1, and I'm adding 1. So this here better be h minus 1 or h minus 2. Otherwise, let's say that it was h minus 5, add 1, I get h minus 4. Sorry, it doesn't work, okay? So that's the only way to make it work. It needs to be h minus 1 or h minus 2. So yeah, so it has to be balanced to h minus 1. That's essentially the argument, okay? So since it's greater than or equal to this, well, that is equal to h minus 1. So I have number of leaves greater than or equal to 2 to the h minus 1, check mark, okay? Okay, so that's an interesting theorem, right? I finally found a really good kind of exponential lower bound, okay? And I want to make that claim a little better, okay? So here's how I will do that, okay? I'm going to use this lemma. I'm not really going to prove it. I'm just going to tell you that it's true, and I might ask you to prove it, okay? But what I'm saying is this. If T is a binary tree that is balanced with height h, right? And remember what that means. It means that inside the balance, that's the h that I used to say, claim that it was balanced, right? Then the height is either h or h minus 1, okay? That's actually just an easy structure in T. It's like I showed you in the previous slide, okay? But the reason that I wanted to do that is that now I can state my theorem a little bit more strongly. Suppose that B is a binary tree that is full and balanced, right? I no longer need to use that h because that h only applies to balanced, okay? Instead, I will use h of t. That's the actual height of the tree. And what I have is that NL of t, the number of leaves, is greater than or equal to 2 to the height of the tree minus 1, okay? So let's see why. Well, I know that h, right, you know, it has to be either the height of the tree, right, or the height of the tree minus 1. So I can just take two cases, right? So height of the tree is equal to h. Well, then the number of leaves is 2 to the h minus 1, right? That's what we did in the previous theorem. And that actually is 2 to the h of t minus 1. So great, right? That works, right? What if the height of the tree is h minus 1? Well, in that case, I have that the number of leaves is 2 to the h minus 1 is greater than or equal to that, right? Well, that's actually equal to 2 to the h of t, which is greater than 2 to the h of t minus 1. So it works in both cases, right? So this is actually a nicer statement of that theorem because I don't need to remind you about that what that h means in balance. Just simply height of tree, okay? So great. This is a slightly nicer phrasing of the theorem. Okay? Now, that's actually as good as we can get, and this is a proof of that statement, because here the height of the tree, right, is actually equal to 1, 2. Okay? And the number of leaves of the tree is actually equal to 3. Okay? So what we have is that the number of leaves is greater than or equal to 2 to the height of tree minus 1. Okay? That's equal to 2. Right? If I actually had something more here, like 2 to the 2, then I get 4, and that's no longer the case. Okay, so it's about as good as I'm going to be able to get. So that's a fair bound. As before, you can expect that I can actually prove this in ACL2, and here's how I can do it. I have to define what it means to be balanced. Okay, so here's the definition. It actually is probably the most subtle definition we're going to have, because what we're going to say is this. Maybe it's well, actually, let's start with this case. What if it's the empty tree? Well, if it's the empty tree, then the only way that it's going to be balanced is if h happens to be equal to 0 or equal to 1, right? Because remember, it's balanced with respect to h, okay? Otherwise, I need this condition, right? And the condition simply says that we're balanced left branch and the right branch, okay? And that's the only way it'll work, okay? So that's it. If I either have a left subtree or a right subtree, then both of those subtrees have to be balanced with respect to h minus 1, okay? And finally, if I'm looking at a leaf,
to understand the question I heard.
So if I'm looking at a leaf, then h has to be either 0 or 1. That's just like the empty case, okay? So that's what it means to be balanced with respect to one of these. Now, once I have that, then I can introduce the theorem, but actually I'm going to need to use a couple of lemmas, okay? So the first lemma that I'm going to have is this. Suppose that it's balanced to h, then yeah, the number of leaves of the tree is greater than or equal to 2 to the h minus 1. Okay, that's kind of the first theorem that we proved. And then we have the second lemma, okay? And the second lemma tells us that the height of the tree is either h or h minus 1. Remember, we claimed that, right, when we're doing this by hand. And so finally, here is the main theorem. And what it tells us is the number of leaves is less than or equal to 2 to the height of the tree minus 1. And we proved that by using these two lemmas. So I actually have to give it a hint, which I didn't have to before, right? So this is actually harder for ACL2 to find the proof by itself. All right, that's all nice, but I kind of want to just point something out, okay? We had that the number of leaves of the tree, right, is at most, okay, 2 times the height of the tree. Okay, it can't be any bigger than that, right? We proved that. That was the first thing we proved, and we were pretty happy about that, right? And now what we're showing is that it's at least 2 to the height of the tree minus 1. Okay, now this is a gap of times 2, right? So it's not exactly a small gap, right? But it does show us that the number of leaves has to be inside this range, right? And that's actually as good as we can get, because, you know, I can have a tree that looks just like that and then just one node, right? That's going to make it close to this, right, to the lower bound. Or it can actually be just like that, and these are all the leaves, right? And then it's going to be close to the upper bound, right? And, you know, other full and balanced trees are going to be somewhere in between, okay? So that's actually an excellent result. We couldn't have done any better.